Hey, what's up YouTube? So here we are back again for some more HVAC optimal start. Okay, so if you're new to this, we are studying mechanical engineering theory on the mathematical models that it takes to condition zones in HVAC when the building sits off all weekend or overnight, and if the weather is extremes, winter or summer, the building temperatures drift inside, and um, it takes a while to condition the building, for its occupants. So, like, what we're studying is the mechanical engineering theory to optimally start the HVAC system, which can be an incredibly powerful energy conservation measure, because usually buildings run way too long before people even get there. So, and we're going off of the research that PNNL wrote a couple of years ago. So please read the paper. It's in this paper subdirectory. It's really good. So there's 4 models. We've covered 2 of them so far. And I actually want to step back on, so in the repo, see the link. So we were looking at linear models, and then we got into the quadratic model, and now we're up to a linear model that has a weather adjusted ratio, the PNNL model 2. And I actually wanted to look back on day 20, this sensitivity check. So this, in the paper, they describe this T reference. This is in degrees Fahrenheit. There's also metric conversions too. I think they used 0 for like a heating T reference. So it's actually it's a ratio basically that will give the math model a little bit extra time in minutes ultimately. So if the ratio is if the outside air weather is very cold as compared to like yesterday, in theory we would give the building a little bit extra minutes, which makes sense, right? So like what I was really screwed up on though, like because I live in northern, I live in the upper USA, towards the Canadian border. So this T reference for a cold climate, that's actually a very mild day in degrees Fahrenheit, where I live, where quite often this goes to 0 degrees Fahrenheit, and even it would be on the extreme side, but it wouldn't be that uncommon to see upper Minnesota near the Canadian border, upper Wisconsin, minus 32 in the middle of the night, even 5 a.m. before that building starts up. Upper Minnesota, even Alaska could see minus 40 in degrees Fahrenheit. So with this T reference that really highlight this, like what I noticed when we were testing the code on the last video, is that it causes the ratio to go in the opposite direction, where we talked about inverting the ratio, but that was correct. So I'm kind of walking back on that last video. So I wanted to simulate this again. So basically, so this is just like a little bit more code that calculates the ratio, same way we did before. And then this is the baselines for heating and cooling. And like I wanted to just say like this ratio of 32, which PNNL used, and then like what I want to set it as minus 40. So that would be anything colder than that would actually have an negative effect on the ratio, but I don't think we'll ever get that bad. And same thing with the heating. We would want to crank that up in degrees Fahrenheit to 110, because that would be a very extreme cooling application. Okay, so I just wanted to like step through this code. Like when we run it, So the ratio, which some of the lessons talked about as we approach these T refs that the paper defines, that will cause our ratio to explode or even reach infinite. So we don't want that to happen. So unless we crank that up to like very high or cold value, that's theoretically won't ever exist, then it's fine. So when I put my model to -40, our ratio does start to explode, but that's fine because we'll never get there. And yeah, I just wanted to show that. So I am going forward to actually using extreme high and low limits that are almost like design day parameters in HVAC. Else this mild value of 32 can have some adverse effects. So this works. This is what I'll be using in my optimal start algorithms, which I'll show you in a minute. Another thing I think worth showing you is so if we look at like an map of ASHRAE, at least in the United States, this is the coldest zone. So HVAC systems are designed to maintain -40 something degrees Fahrenheit near the Arctic Circle. I'm in zone 7, so, and also I'm also in between these zone 7s, 6A, 5A. So in the United States, there's a variety of different weather patterns here, mostly because in this area we can experience a lot of humidity in the summer, so high humidities, and also very cold winters. Here, not so much, very dry in this part of the world. In Florida, this is tropical, and also the bottom of Texas, as with Hawaii. So there's a wide variety of temperatures, high and low. So PNNL, where they did the research, they're out here. So this would be more of probably European climates, where maybe England would have a really similar pattern to British Columbia, Canada, where a lot of same thing with parts of Alaska here. Kind of a very mild, temperate, coastal rainforest climate. But here in the interior, as with Ontario, Quebec, Canada, we might see some really wild temperature extremes. I'd also be really curious what Australia sees for their weather patterns. Maybe on the Gold Coast, you're about sitting more I'm just guessing, you're just sitting more of this Georgia climate. And if you get more towards Papua New Guinea, I can't remember the couple of the cities up in Australia, up on top, they're getting more into this subtropical climate. So I think just my point is that it really should make a big difference in what you use. So I think that will end with covering model 0, 1, 2, and 3. The next thing, I might even do this for maybe the next video. I think we'll be starting on day 22. This will be model 3. So in the white paper, this was actually the model that performed the best out in scenarios where outside air temperature kind of impacted it the most. So just noticed my little mouse highlighting tool isn't working, so maybe I'll restart it. There we go. So maybe we can start this tomorrow if I find some time to record some videos tomorrow. So another thing I wanted to show you is something I've been thinking about in Vibe Coded a little bit, is the Vibe Coder repo for the Niagara program objects, which is all Java code. I've actually been here, let me just show you this in Workbench. So this is more of like production ready building automation optimal start code. Like we covered before in really earlier videos, the Niagara building automation system comes with a really primitive optimal start block, which would be model 0, but we've been kind of getting through these more fancier mathematical models, the PNNL model 1 and 2. Just to recap a little bit, like I'm just highlighting here because this is actually a block that incorporates all 3 models inside of it. So model 0 is actually the linear model, degree per minute. Model 1 is the quadratic regression, based on the zone based on the zone recovery data of the zone temperature data. And model 2 is it basically is model 0 degree linear degree per minute, but also including the ratio to factor in weather. So essentially, like what this block will do has all 3 mathematical models running inside of it. These metrics, you can see like what the parameters are actually calculating to. And I think I'm to the point where I can deploy this in the field, so I'll probably do that a little bit tomorrow, and maybe sometime in the future we can actually see what it's doing. I'm really curious to see this. So basically, in the real building automation world in Niagara, this is a fake equipment run schedule. So the building operators do this in the field, so they want their buildings to operate from 7:30 to 4:30, and what I talked about before is the building operators start doing this. They start doing this crazy operating hours for the building, just because they don't care if the building saves energy. They get graded on how many temperature complaints do I have. So if I run HVAC really long, it burns a ton of waste of fuel. They don't pay the utility bills. They don't even see it, so that's why they do it. So we're working on these optimal start algorithms where people come into the building, let's say here and here, and we're calculating that optimized time delta so they don't have to do that. So on here in the Niagara world, so this would be wired to an equipment start command. So this equipment is outing a value of true, which we wire in at a value of 16, which is lowest priority. Then a higher priority is wired to our equipment out command. So if so what our block is doing is like we're feeding in the next time that the building automation schedule changes state. So like in here will be our value of true is occupied, and then value of false is unoccupied. So our optimal start algorithm has to look at that. So it's only interested in when the next value is true. That means when the building is occupied. If the next value is true, we're in the middle of the night, before the building starts up, that's when our math algorithms will start predicting, that's time delta right here of like the time in minutes it'll be required to warm up or condition the zone. So that's why the optimal start algorithms always have to know next value and next event time, where in Tritium they calculate it to the milliseconds, which is a bit overboard to me, but that's what they do, so we'll follow it. So we're also incorporating in building automation, there's an occupied cooling set point and effective occupied heat set point. So this is typically a zone set point with deadbands factored in. So when I deploy this block on the live building automation, I'll copy it into a wire sheet, and then I'll link these to the actual points. And then this code here actually calculates a target zone set point, and then it's also calculating the deadband here, which is like a temp tolerance, is something that I've been calling it. So if these ever get adjusted by the building operators or the tenants, that this little math right here will account for that. So there's another point that enables the block, else this is always null. The maximum minutes allowed. So back in the schedule, there's a parameter here that it only allows a maximum. I have it defaulted to 75 minutes. So if the models predict more than 75 minutes, it caps it at that. That's what that is. Temp tolerance, history days to retain. So that's 14 days of performance history that we record. Here's our smoothing factor for EMA. This is actually just a delay parameter in here that I just want to talk about more time. So like if we optimally start the building and then we kind of drift into this actual real occupied state, that the block knows that, and like it'll have a 100-second delay before it releases it back to null, which the real building automation system will take over. So like what our block will do is it'll output true right here, and after the real building automation schedule changes state to true, so these would both be true for 100 seconds, and then a timer expires and it releases back to the building automation after 100 seconds back with null. So okay, so like with all of this is where I'd wired outside air temperature. So like what I'm using in here, we can talk about the Java code later, I think, like, and just maybe watch this in time. I'm like dying to see if this will work. So like the block will use model 0, which is the linear degree per minute, for 3 days, and then it'll control to linear degree per minute model 0, and calculating minutes required to condition the zone. And then after 3 days, basically the block will start also trying to calculate model 1 and model 2. So after 3 days, it goes into like an auto mode. So if we start getting better performance out of the models, it'll switch to that model 2 or model 1, or if model 0 is still performing the best, it'll keep it locked in at model 0. And it'll do that based on the average squared error. So we talked about before in previous lessons that we want to be controlling, or we want the models to optimize to average squared error. So our squared error here is minutes, basically, is that the actual minutes that it took to condition the zone to modeled minutes, and then our last run squared error for model 0, model 1, model 2. So we'll be saving those in a data structure for 14 days. So we only save on a rolling basis 14 days of data, and then we'll take an average of that data in that array, and that'll be our average squared error. So which model has the lowest average squared error, we'll use from that point on. And I'm really curious to see. I've actually been playing around with a primitive version of model 1, and I've seen it get some really precise results and also some really off results. So I'm curious to see what this will look like in time. And remember, in time, at least where I live, the weather is constantly fluctuating, especially in upper Midwest, near the Canadian border. So we could get -40 one week, and then the next week it'll be +40. degrees Fahrenheit. So that would be kind of an extreme example, but it happens. So this self-tuning models will hopefully adapt for that. It'd be really interesting to see too if the block will switch depending on which model has the best squared error for whatever's going on outdoors, if your zone is really affected by weather. So I'm dying to see how this works. So like, here's some metrics to trend, which I might try and do on the building automation, is like which model is currently being used, the average squared error for model 1 to model 0, 1, and 2, which we'll ultimately see here as well. So this is it. This is what I'm really curious to see. There's a ton of Java code here that makes this all happen in some computer science patterns. So the computer science algorithm is constantly checking this. And then when the condition is true that our modeled time delta is less than the actual time delta that the building comes occupied, that's when that computer science pattern triggers the equipment run command to start early, and it'll start logging the zone temperature, outside air temperature, and the effective minutes that it took to warm up the zone, even if the zone warms up earlier than modeled or even later than modeled if we're into the occupied building. That is it. So this is what I'll be deploying in the field. Maybe I'll record that on YouTube too. This is a kind of work in progress, and it's been kind of fun too. So if you're following along, thank you. And I also have some PhD friends. Some are students, so they're also supposed to be following along, especially in the mathematical modeling world. If you see something that looks funny or suspicious, please contact me or flag it that you're doing something wrong. So kind of learning here in a community effort. And if you want to actually see this on the Vibecoder repo, which I'll post. So this is just our linear model using the linear EMA. So our alpha parameter, our rate new is basically this is a classic exponential moving average code right here. So this is model 0, essentially our baseline model, where alpha is the learning weight, it's tunable, larger alpha or else. So this is a little bit about the alpha parameter, and then we predict our optimal start time using this. In model 1, our quadratic recovery model, interior for more, the paper says to do it for more interior based zones that don't have outside air temperature. So this is basically our time in T is our alpha parameter times our zone temperature squared, which we've talked about this in previous lessons, that it's our alpha parameter times our zone temperature delta, so that's zone temp minus the occupied heat or cool squared times a B alpha parameter times degrees delta temperature again plus a C parameter. So like units for this parameter ultimately are degrees, our delta temperature degrees squared per minute, and then this is degrees, and then this is just a minutes. So when you solve for T, which we did on the other videos, we solve for each one of these parameters. In the previous videos, that's which also the Java code does too. That's what happened. So like, then here is our model 2. Just a little refresher. This is the last 7 days that we've went over. Here's our baseline model time. So this is basically the same thing that we're doing here. So it's just taking this same model 0 parameter and then applies this outside air temperature weather ratio that I talked about at the beginning in here, that we so the beginning of this video where we talked about the weather ratio, that's this. So can't wait to see how this works. So and then the model selection, this is our error, so that's what we talked about. Whichever model has the best average squared error is the winning model. So this is a little bit about the Niagara slots, or those parameters that I showed. And then if you want to see the full Java code, it's also here in the README. You can view it in the browser, upload it to AI. It's meant to be uploaded to AI. So yeah, it just has these -40 constants, -110. So kind of cool to look at this. So I did a lot of testing in the office and a lot of validating this. So this is it's a lot of code, but it is kind of cool that you can write code in Java in these program objects. I think it's really cool to do. This is something I'm actually deploying in live building automation. It's like training wheels almost for if you were a developer, you're kind of in this little safe sandbox environment. So this is we're actually calculating the code here, T1, T2. So it's kind of fun. So this is like computer science patterns for monitoring active run, which we talked about, and how we calculate some of our metrics. It's very important. So yeah, they're full of what quadratic regression that's happening under the hood. That's and I also want to point out here that these are just kind of lightweight in building automation. It's all kind of lightweight math that this can handle. There isn't like full-blown machine learning or anything, or really complex math going on here. It's just a little simple, like all we're doing, the most complex thing we're doing here is we're adding, we're multiplying, and we're doing to the second power, or cubing here. So it's just pretty simple math. I think from a computer science perspective, like this is our solving our quadratic regression coefficients for our equation. So this is as fancy as it gets, as multiplying a number, subtracting a number, multiplying again, and dividing. So as we get into these more, let me get back here. Whoops, sorry. When we get back into these, I must have closed out of the other window, but like in the PNNL papers, once we get into the more Model 3, Model 4, and conceptual Model 5, I don't think that I'll be doing anything in program object anymore, because next couple days we'll see this. It's like these more fancier math models require linear algebra, kind of some fancy multiple regression mathematical libraries, which I'll do in Python. So that is not available in these program objects. We're just doing simple math, like I showed you before. So I think I'll probably end up stopping this will probably be it. I couldn't imagine. I'm not really 100% sure on that. I'm like 99% sure that like we'll just be doing Model 0, 1, and 2. But I'm really curious even to see what this looks like. So I think that's it, guys. I just wanted to show you this, where I'm at here with this on the Vibecoder repo. I'm calling it, these were separate program objects to run Model 0, Model 1, Model 2, but I just came up with this idea out of to make the ultimate HVAC optimal start, which includes all of the models. So I think it'd be really cool if there was like a Niagara developer out there. Like you could actually, maybe this would be like a neat starting place for to build like a real Niagara module with Java linear algebra libraries or Java, multiple regression. How you can do that with make it easy with better libraries available. So maybe this would be like a neat place for someone that could take all this Java code and lessons we've learned here that they could even run with creating, something, more advanced than what comes out of the box with Tridium. Maybe even Tridium could update it to their most. That would be really cool because I know they haven't changed what comes out of the box with Tridium. That hasn't been updated, to my knowledge, since Niagara AX, which date back to 2005, which is 20 years old. So I think that's it for today, guys. So follow along for the next couple of weeks here. We got models 3, 4, and 5 to still do. So thanks for watching so far. If you've been following along, be sure to like and subscribe. Talk to you later.